Good morning all. So in today's lecture, let us know about natural radioactivity. So nuclear physics is that branch of physics which deals with the properties of nucleus. So before going for the properties of nucleus, the structure, radius, etc., let us in this lecture let us know about natural radioactivity. So in 1896, Henry Becquerel, he wrapped uranium in a black paper and placed it in his table drawer. In that table drawer, he even kept some photographic plates, some other files, etc. And he just forgot about this uranium which he kept in his table drawer. After some months, he needed a photographic plate and he took that photographic plate from that table drawer. When he saw the photographic plate, it is affected by, he found that it is affected by some rays or radiations. Okay. Then he searched his table drawer. He found uranium wrapped in black paper. He did experiments on this uranium and finally his experiments showed that this uranium will emit certain radiations. That radiations can affect a photographic plate, right? So now these radiations which are emitted from the uranium are alpha, beta, gamma radiations. These radiations are highly penetrating. They ionize the gas. They cause scintillations on fluorescent screen. Okay. Now after 2 years, Pierre Curie and Marie Curie, they took pitch blende ore of uranium. Okay. Now they did experiments on this and they found that these substances will emit more intensified radiations compared to that of uranium, and they named this substance as radium. Now the substance which emit the radiations spontaneously, we call it as radioactive substance. The spontaneous emission of radiations, we call it as radioactivity. Some of the examples for this radioactivity material are uranium, radium, radon, polonium, etc. And here the spontaneous emission of radiations, that is alpha, beta, gamma radiations, takes place for the substances whose atomic numbers are greater than 82. Right? Now next, after some time, Rutherford with his co-workers discovered the nature of these nuclear radiations. So Rutherford discovered the nucleus. One day he was doing the experiment on gold foil. He wanted to know how the alpha particles will behave when they pass through the gold foil. Surprisingly, he found that some of the alpha particles are bounced back. Some of the alpha particles go straightly without deflection, and some of the alpha particles undergo lesser deviation. Okay. So from this, he concluded that the rays which are bounced back means there must be some positive charge present at that place. Okay. So now this in atom, this positive charge, I think you all know the structure of atom. Atom means the protons will be there, electrons will be there. right? So according to Rutherford's experiments, he founded that all the positively charged protons concentrate at the central core of the atom. So only as alpha particles are positively charged particles, when they move towards this concentrated area of protons, they bounced back. So that bouncing back clearly showed that all the protons will concentrate at one particular point, and that he named as nucleus. Alright. Now next, Rutherford and his co-workers just did some experiments, that is they applied the electric as well as magnetic field to this radium and tried to find out the nature of these nuclear radiations. So now here first they applied the electric field. Okay, so they kept radium in lead block. Okay, now next they applied electric field, a positive plate and the negative plate to which the external source is connected, a positive plate and negative plate. They found that some particles are attracted towards the negative plate, some particles are attracted towards the positive plate, and some particles went undeflected. So particles which are deflected towards the positive plate, they named it as beta radiations. The particles which deflected towards the negative plate, they named as alpha particles, and these undeflected radiations are named as gamma radiations, right? So now here alpha particles means the experiments proved that alpha particles are nothing but doubly ionized helium atom. Okay, and beta particles are nothing but fast moving electrons that emerge out from the nucleus. Okay, these are the electrons coming from the nucleus, the fast moving electrons coming out from the nucleus. And gamma particles are nothing but the photons, electromagnetic radiation. Okay, similarly again they applied magnetic field. Here also they found that the alpha and beta particles are deflected and gamma particles remains undeflected. Right? Now next, let us go for the properties of these radioactive radiations. Okay, so first let us define what are alpha, beta and gamma radiations. Okay, so here alpha radiations means, as now only I said, doubly ionized helium atom. We call it as alpha radiations. And beta particles means nothing but fast moving electrons originated from the nucleus. And gamma radiations means nothing but electromagnetic waves or electromagnetic radiations which are nothing but photons of very short wavelength. Right? Now if we take the electric and magnetic fields, then these alpha radiations are deflected by electric and magnetic fields. Beta radiations are also deflected by electric and magnetic fields. And gamma radiations remains undeflected. Gamma radiations, they remain undeflected. Okay, now next if we move towards the velocity, then the velocity of alpha radiations range from 1/10 to 1/100 of velocity of light. If we take the velocity of beta radiations, their velocity will be 1% to 99% of velocity of light. Now if we take the velocity of gamma radiations, the velocity of gamma radiations, they are nothing but, I said, photons. So they travel with velocity of light 3 into 10 to the power of 8 meters per second. Alright. Now if we take how they affect the photographic plate means, the alpha radiations, they affect photographic plate very feebly, means less. Now if we take the beta radiations, they also affect the photographic plate, but with much higher degree than alpha particles. And gamma radiations, they affect photographic plate more strongly than beta rays. Alright. Now next, let us see whether they produce fluorescence or not. Now if we take the alpha particles, then they produce fluorescence on zinc sulfide, barium platinocyanide, etc. Beta particles also produce fluorescence on barium platinocyanide, calcium tungstate, etc. And gamma radiations produce fluorescence in certain crystals. Okay, they produce fluorescence in certain crystals. Now next, let us talk about the ionization power. The ionization power for alpha particles will be very intense, that is very more. And the ionization power for beta particles will be 1/100 of alpha particle. So what is ionization power? So that power of that particular radiations which can break the atom into ions. If we take the example of NaCl, Na plus Cl minus. So the capacity of the radiations, or the ability of the radiations that can break the atoms into, or molecules into ions. Okay, molecules into ions. So as alpha is having high mass, its ionization power is more. As gamma radiations are nearly massless, its ionization power is feeble. And if we talk about the penetrating power, so alpha particle has lowest penetrating power. Now beta particles have penetrating power more than alpha particles, and gamma radiations have intense or highest penetrating power. Penetrating power means entering into any substance or metal or sheets. That we call it as penetrating power. Right? Now next, already up to now whatever we are discussing is about natural radioactivity itself only. So what is natural radioactivity? So natural radioactivity means the spontaneous emission of powerful radiations. The spontaneous emission of powerful radiations by heavier elements whose atomic number is greater than 82. Heavier elements founded in nature. Then what is artificial radioactivity? So artificial radioactivity is also nothing but spontaneous emission of these radiations by some modern techniques of artificial transmutation of element. By using some modern techniques. Here spontaneous emissions of elements much lighter than those occur in nature. By modern techniques of artificial transmutation of element, we call it as artificial radioactivity. Alright. Now next, let us go for the radioactive disintegration. So first let us know what is disintegration, and then let us go for the laws of radioactive disintegration. So disintegration means one atom changing into another atom. That we call it as disintegration. So disintegration is nothing but one atom changing into another atom. That we call it as disintegration. Right? So now first let us discuss about alpha decay. Okay? So spontaneous breaking up of nucleus. We can say the spontaneous breaking up of nucleus. That we call it as radioactive disintegration. Okay? So now here first let us discuss about alpha decay. If a radioactive element disintegrate by emission of alpha particles, which is nothing but doubly ionized helium, that is 2He4, where 2 is the atomic number, 4 is the mass number. Alright. So here XZA, we call Z is the atomic number, A is the mass number, we call it as parent nuclide. By emission of alpha particle He24, it converts into new nucleus. This new nucleus formed, we call it as daughter nuclei. And daughter nucleus atomic number reduces or decreases by 2, mass number decreases by 4. If we take an example, U92-238, by emission of alpha particle, it converts into new element daughter nuclei, which we call, that is thorium. So 92, that is Z minus 2, 92 minus 2, 90. A minus 4, 238 minus 4, 234. Thorium 90, 234 plus 2He4, which is nothing but alpha particle. Now next let us move for beta decay. So if a radioactive element decay or disintegrate by emission of beta particles, we call it as beta decay. Atomic number here increases by 1, mass number remains unchanged. XZA gives YZ plus 1A with the emission of beta particle minus 1, 0. The charge is negative charge. Okay. Now let us take the example of thorium 90-34. So atomic number is increased. Atomic number, it is increased by 1. Okay. So as atomic number is increased by 1, it becomes Z plus 1, 90 plus 1, 91. Protactinium. And mass number remains unchanged. So Pa 91-31 plus beta minus 1, 0. Okay. Now next, gamma decay. Okay. So if element disintegrate by emission of gamma particles, here mass number or atomic number remains unaffected. Now if we take the X, now how the gamma particles are formed, emitted. How the gamma particles are emitted means, when the higher nuclei from ground state goes to the excited state. As excited state is unstable state, again this element return back to the ground state. While returning back to the ground state, it emits certain radiations. That radiations itself only we call it as gamma radiations. Now if this is the ground state and this is the excited state, first the element moves from ground to the excited state. As excited state is unstable state, it returns back to the ground state. While returning back to the ground state, they release or emit the powerful radiations. We call it as gamma radiations. If we take an example of barium 56-137, now it emits gamma radiations while returning back to the ground state, and the atomic number as well as mass number remains unaffected or unchanged. Ba 56-137 plus with the emission of gamma radiations. Right? Now next, let us discuss about now the laws of radioactive disintegration. Okay. Now the first law we call it as displacement law. The first law we call it as displacement law. In 1913, Soddy and Fazans, they both discovered this law. So as now I said, in all non-radioactive transformation, either alpha or beta particles are ejected by the atom. If alpha particle is ejected, mass atomic number reduces by 2 units, mass number reduces by 4 units. If beta particle is ejected, atomic number is increased by 1 unit and mass number remains unchanged. Now the examples: uranium 92-238 converts into thorium 90-234 with emission of alpha particle He24. And if we take the example of beta ejection, thorium 90-234 gives protactinium 91-234 with emission of beta particle -1, 0. Alright. Now next, the second law says that disintegration is at random. The second law says that disintegration is at random. So disintegration is at random means which atom will disintegrate first is matter of chance itself only. We cannot say that this atom, that atom will disintegrate first. It is just the matter of chance. Any atom can disintegrate at any time, just a matter of chance itself only. Now the next one is law of radioactive decay. The next one is the law of radioactive decay, right? So the law of radioactive decay says that number of atoms that disintegrate per second is directly proportional to number of remaining unchanged radioactive atoms present at that time. That means, for example, if n is the number of atoms present in a radioactive substance at any time, let it be 100, let us think, right? Now the atoms have started disintegrating. Let Dn be the disintegration of atoms in some short interval of time dt. Okay, let us assume that out of 100 atoms, 50 atoms has disintegrated. Then radioactive law says that this disintegration rate is directly proportional to, now how many remained here? Out of 100, 50 disintegrated. So 50 atoms remained here. So he is saying that rate of disintegration will be directly proportional to the atoms remained at that particular time. So negative sign indicates the decaying process. Okay, so minus dn by dt proportional to n, or minus dn by dt is equal to lambda n, where lambda we call it as proportionality constant, that we call it as disintegration constant. Now doing certain mathematical calculations, we get n equal to n naught e to the power of minus lambda t. Now this gives the number of atoms given in radioactive substance. Okay, and it says that it decreases exponentially. Okay, it decreases exponentially with time, provided no new atoms are involved. Alright, now this is about law of radioactive decay. Now let us define what is decay constant. Right, so now here decay constant means from this minus dn by dt equal to lambda n only, we are writing lambda equal to minus dn by dt by n. That is the ratio of amount of substance disintegrated in unit time to amount of substance present at that instant. Or we can also define this decay constant as, if we assume t equal to 1 by lambda, we get n equal to n naught e to the power of minus lambda. In place of t, I am substituting 1 by lambda. Lambda strikes off, e to the power of minus 1 we will get, that is n naught by e. The value of e is 2.718. So n naught by 2.718. So n is approximately equal to 0.37 n naught. So it indicates that here at t equal to 1 by lambda, n is reducing to 37% of original atoms or initial atoms present. right? So that we call it as decay constant. So decay constant is nothing but the reciprocal of time. T equal to 1 by 2 lambda, no. So lambda equal to 1 by t. So it is nothing but the reciprocal of time, where the number of atoms of a radioactive substance falls to or decrease to 37% of original value. If 100% is 100 atoms are present, then at this particular time, that is at t equal to 1 by lambda, what is happening? In that 100% atom, 37% atoms are disintegrating. That we call it as decay constant. Now next, half-life time, right? So half-life time means what? In particular time, if out of 100 atoms, it reduces to 50 atoms, that we call it as half-life time. The time in which 1/2 radioactive substance is disintegrated. How much time is taking for a radioactive substance to disintegrate to its 1/2 value? If 100 atoms are there, then how much time it is taking to disintegrate into 50 atoms? 1/2 of a radioactive substance is called half-life time. Now n equal to n naught by 2, if we substitute in this formula n equal to n naught e to the power of minus lambda t, how we get half-life time equal to 0.6931 by lambda. Now uranium half-life time 4.5 into 10 to the power of 9 years. Radium half-life time 1620 years. Radon half-life period 3.8 days. Okay. Similarly, polonium half-life period 10 to the power of minus 7 seconds. Now mean or average lifetime of radioactive elements. It is defined as sum of lifetimes of all atoms divided by total number of atoms. So Ta is equal to 1 by lambda, and the reciprocal of disintegration constant we can say it is nothing but the reciprocal. After certain mathematical calculations, we will get Ta equal to 1 by lambda, and we can define this mean or average lifetime of radioactive substance as reciprocal of disintegration constant, that is T of equal to 0.693 Ta. This is the relation between the half-life time and average lifetime. Okay, so we can say that half-life period is equal to 0.6931 times average life period. Right? Now next, let us move for activity of radioactive substance. It is nothing but the rate of decay or the number of disintegrations per second, dN by dt mod. Now substituting n value, n naught e to the power of minus lambda t, we get lambda n. If A naught is the activity at time t naught, then A naught is equal to lambda n naught, or A by A naught can be written as n by n naught, which is equal to e to the power of minus lambda t. So A equal to A naught e to the power of minus lambda t. If we compare this with n equal to n naught e to the power of lambda by t, it is showing us that even the activity also like n is time dependence. So we can say that activity is directly proportional to the number of atoms disintegrated, okay, or number of atoms present. Number of atoms present. Now next, if n half life period is there, for example, if n half life period is there, then n is written as n naught 1 by 2 whole to the power of n. Now units of radioactivity is Curie. Curie is nothing but it is the quantity of radioactivity material which gives 3.7 into 10 to the power of 10 disintegrations per second. 1 millicurie, milli means 10 to the power of minus 3. Micro means 10 to the power of minus 6. So the value will be 3.7 into 10 to the power of 7 disintegrations per second. 1 microcurie will be equal to 3.7 into 10 to the power of 4 disintegrations per second. And another quantity is also present that we call it as Rutherford and denoted by RD. It is nothing but the quantity of radioactive substance which gives 10 to the power of 6 disintegrations per second. Now in today's class, our last topic is about carbon dating. Okay, so I think all are familiar with carbon dating. So by using this only we will find the age of fossils such as rocks, mountains, earth, etc. We will find the age of this. We will determine the age of this as well as the fossils. Okay, then how we will do this? How we will do means, in outer space cosmic rays are present. These cosmic rays collide with the atoms in Earth's upper atmosphere, and due to these collisions only the radioactive carbon, that is C614, C612 is normal carbon present in the atmosphere, and C614 is the radioactive carbon produced due to the collision of cosmic rays with the atoms in Earth's atmosphere. Okay, so now how we are getting this means, when a neutron from cosmic rays collide with the nitrogen N714 present in atmosphere, it give rise to the radioactive carbon C614 with emission of one proton, H1H, with one proton. Alright. Now this C614 oxidize into carbon dioxide CO2. Okay. Now this CO214 mixes with, now this C614 oxidizes into carbon dioxide CO214. Now this CO214 again mixes with ordinary carbon dioxide of atmosphere. So the ratio of ordinary carbon C612, radioactive carbon C614 will be in atmospheric carbon dioxide will be 10 to the power of 12 is to 1. So what is this ratio? It is the ratio of ordinary carbon C612 and radioactive carbon C614 in atmospheric carbon dioxide. 10 to the power of 12 is to 1. Alright. So all trees, plants take CO2 from atmosphere, we know that. So in living plants we will have the ratio of the normal carbon as well as radioactive carbon. Both they will absorb, and it will be in ratio of 10 to the power of 12 is to 1. Now let us think that a plant has died. So when plant dead, what happens? It stops taking carbon dioxide, right or wrong, until plant is alive. Until plant is alive, it takes carbon dioxide. When plant dies, it stops taking CO2 from atmosphere. But the C612 which is in its present in its body remains unchanged. After dying, it stops absorbing CO2. But the C612 which is already present in body remains unchanged. Now, and next radioactive carbon C614, it continues to disintegrate. This remains unchanged, but it continues to disintegrate. It disintegrates into nitrogen 714 with emission of one beta particle and anti-neutrino. So it is undergoing beta decay, we can see. C614, it just continues to disintegrate, but C612 which is present, it remains unchanged. So C614 undergoes beta decay. Now the half-life of this decay is 55-68 years. By measuring radioactivity of some dead material like coal, wood, fossils, like a dead material like coal, wood, etc., the age of that material can be determined. So, by measuring the radioactivity of some dead material, the age of these materials can be determined. So, this method of age determination of fossils, we call it as carbon dating. So, here what happens? Generally, the living plants or trees, when they leave, they absorb C612 as well as C614. After they die, they stop absorbing CO2. But the C612 remains unchanged and C614 just continues to disintegrate. By knowing the radioactivity of some dead material, we can determine the age of that material, which we have to determine. So this method of age of determination of fossils, we call it as carbon dating. Alright. So now about mathematical formulas and mathematical part. Now here, up to here, we completed one particular topic, right? We completed one particular topic. Then how to prepare for problems? How to prepare means, first you have to understand the question. Every problem will be asked from the topics which you have read only. First, understand the question. Write down all the parameters which he gave in the problem. And just think which formula is related to all these parameters and apply that formula. So, for knowing the formulas, you must sort out the problem after completing one particular topic. Just sort out the formulas. Now, in today's topic, whatever we read, I sorted out. Now, we read about radioactive decay law minus dN by dt equal to lambda n. Number of atoms in a radioactive substance n equal to n naught e to the power of minus lambda t. Decay constant lambda equal to minus dN by dt n, or lambda equal to 1 by t. Now, next half period time T of equal to 0.693 by 31 by lambda. Mean average or average lifetime Ta equal to 1 by lambda. Relation between T of and Ta is equal to T of equal to 0.6931 Ta. Activity of radioactivity proportional to number of atoms present given in radioactive substance and number of atoms left after n half lives, n equal to n naught 1 by 2 whole to the power of n. In such a way, you have to sort out all the formulas, write down in the notes. Now prepare that formulas perfectly and just read the question given, write down the parameters, see which formula should be applied to that and just do the calculations. Okay. If you like this video, like, subscribe it. Okay. And just stay with my channel Reshma Physics to receive more updates about competitive physics and graduation physics. Thank you.